Welcome everyone to our last lesson in our course of study on Regents physics. Today's lesson is going to be on the standard model of particle physics, our last lesson in our unit on modern physics, which has kind of been a little bit of a different taste of science compared to what we've done throughout the other part of the year. And the standard model of particle physics, like a lot of other things in science, is a theory and is not quite a law yet. Laws generally are proven by many different types of experimentation, whereas theories do not have that evidence available to call it a law. And theories are often changed over time, kind of like we saw with the atomic theory, which changed several times throughout its history. And as more experimentation occurred, there was more information that was revealed, and the theory was then changed to account for that new information. So right now, particle physicists, like our friend Dr. Williams, they're in the process of building the current model of the nucleus, which, since its theory continues to change over time. And we know that now as the standard model of particle physics. And what this theory attempts to do is come up with a new explanation about the nucleus and how everything fits together. As new experiments have occurred and new information has come about, the theory has to be modified in order to explain different particles that seem to be coming up in all these different types of experiments that are occurring. And as more particles get discovered, this model, this theory, has to be altered in order to fit all the information that's coming out of these different experiments. Now, in modern physics, scientists refer to particles as force carriers, since forces are brought about as a result of an exchange of particles. And there are four different fundamental forces of nature. And the strongest one that we learned about recently is what we call the strong nuclear force. And that's responsible for holding particles in the nucleus together, like our protons. Since it's the strongest force known, we're going to give it a relative strength of 1 and compare all the other forces to that strong nuclear force. The range of the force is very small, though. We know that it dissipates very quickly, so it's only effective over a very short distance. The next strongest force is our electromagnetic, which is really 2, which we'll get into in a minute, combined into 1. And it is about 100 times weaker than the strong nuclear force. It's still pretty strong, and it has a more effective range. We know that is proportional to 1 over the radius between the objects squared. That's going to have a greater distance to be effective when compared to the strong nuclear force, although the electromagnetic is going to be a slightly weaker force. Which brings us to our next force, which we call the weak force, which was discovered, and we'll get to in a second here, that is essentially responsible for decay of some nuclear particles, which wasn't really discovered until we started discovering these decay particles that were coming about. This one is significantly weaker compared to the electromagnetic or even the strong nuclear force, and has an even smaller range of force when compared to even the strong nuclear force. And the last one, which is going to be the weakest of the bunch, is the gravitational force, which you can see its strength is significantly smaller than any of these, but still has the same range compared to the electromagnetic. So it can have an effective range to affect other objects, but the strength of the gravitational is not very strong. As we said, the weak force is another short-range nuclear force. So it's not going to have a whole lot of effect over a larger distance. It's only going to cover that real small range, even smaller than the strong nuclear force. And they're responsible for the decay of several different types of nuclear particles. And until we started learning about these decay particles, we didn't even know that the weak force really existed. Now the electric, we dealt with these separately this year, electric and magnetic. And then we talked about combining them. We often treat them independently, but they're actually combined as one, as the electromagnetic force, which we talked about in Unit 8. Now, this model of particle physics has a lot to do with different subatomic particles that are fundamental to create larger particles. Now, these particles can be classified according to their types of interactions that they have with each other. So depending how they're going to behave with each other, they're going to be classified differently. And if we get rid of and don't account for the force carrier particles, we can classify all the particles that we know into two different groups. First one is called hadrons. Make sure that's a little bit clearer and we can read that. Hadrons, they're particles that interact through the strong nuclear force and the electromagnetic and the weak and the gravitational forces. So a couple examples are protons and neutrons. They're large enough, have a charge, or in the sense of neutrons, they wouldn't, but they would react or come under some type of force, interact with each of these types of forces. The other group are what we call leptons. And leptons are particles that are going to interact through the electromagnetic, weak, and gravitational forces, but not the strong force interactions. A lepton has a mass that is less than that of a proton. And electrons, positrons, and neutrinos, it's a new one, are leptons. And we know a positron is really the antiparticle or the antimatter form of the electron. It has the same mass as the electron, but it has a positive electric charge that's equal in magnitude to the negative charge of an electron. So it's equal magnitude charge, but in opposite directions. The neutrino is a neutral particle that has little, if any, mass, but it does possess energy and momentum, which is one of the things that is kind of confusing, because if you don't have any mass, how can you possess energy and momentum? These are one of the many things that we try to modify our theory to fit and understand more where we can. Now the hadron group, can be subdivided even further. We can subdivide it even further into groups called baryons and mesons. Now, a lot of what we're going to cover here is a lot to do with classification and understanding the different names and how they fit in with each other, but the idea behind them is not particularly difficult. So we have two different groups of hadrons, baryons and mesons. Now, a baryon, to start, is an elementary particle that can be transformed into a proton or a neutron. And then we'll have some other number of some mesons and some other lighter particles as well. Baryons are also known as heavy particles because their mass is equal to or greater the mass of a proton. Now, a meson is going to kind of fall in the middle. They're particles of intermediate mass, and they may decay into electrons, positrons, neutrinos, and also photons. Now, these are all of our subatomic forms of matter, which we can break down even further, and we will do shortly. But before we do that, I want to talk a little bit about antimatter. And in the standard model, we have antiparticles, which make up our world of antimatter. So an antiparticle is associated with each particle. An antiparticle, if you know the particle, then you'll pretty much know the antiparticle. It's a particle having mass, lifetime, and spin identical to the associated particle, or the form of matter, not antimatter. But it's going to have charge of opposite sign if it is a charged particle, and magnetic moment reversed in sign. And the antiparticle is denoted by a bar over the symbol for the particle. So to give you an idea here, a couple examples. We know that a proton is represented by P, letter P, and the antimatter form is represented by pi with a bar over it. Now the antimatter form here, the pi symbol with the bar over, actually has a charge of -1 compared to the proton has a charge of +1. And the masses are equal. The neutron we represent with a lowercase n, and the antiparticle represented with a lowercase n with a bar over the top. Now for each of these, both of these are neutral, and they have the same mass. But if we think about their spin and magnetic moment, and the neutron, these are going to be in opposite directions. The spin and magnetic moment are going to be in opposite directions, whereas in the antiparticle neutron, the spin and magnetic moment are going to be in the same direction, whether that's both up or both down. It's kind of arbitrary, it doesn't really matter. But they're going to be in the same direction. For the electron, we denote that with a symbol with a lowercase e. And the antiparticle electron, you might remember this from chemistry, is a beta plus, which is otherwise known as a positron. Equal in mass, same mass, but charges are going to be opposite. Masses are equal, even though they are still extremely small. Now, antimatter, we just talked about antiparticle, but antimatter which we're hearing more and more about every day as we discover more about this model of physics. Antimatter is material consisting of atoms that are composed of are antiparticles. So antiprotons, antineutrons, and positrons. So those are going to make up the antimatter that we know of. Now, to break down our hadrons a little bit further, we're going to talk a little bit about quarks. And this can be a little bit quirky, especially some of the names. And you might remember some of these from last year. We touched base on these a little bit in chemistry. But baryons and mesons, which are our two classifications of hadrons, are composed of more fundamental particles, which we call quarks. Now, a quark is one of the basic particles having charges of either plus minus 1/3 e or plus minus 2/3 e. And these quarks, using a different combination of these quarks, we can build up any of our elementary particles. And there were 6 different types. You might remember some of the names from last year or coming across them in your reference table. They are called up, down, charm, strange, top, and bottom. So a combination of these 6 different quarks are going to allow us to build up any of our other elementary particles. So every baryon is a combination of 3 quarks. And every meson is a combination of a quark and antiquark. Now, an antiquark is the antiparticle of the quark having an electric charge, baryon number, and strangeness that is going to be opposite in sign to that of its corresponding quark, similar to what we know with all the antiparticles. Now, an antibaryon consists of 3 antiquarks. Now, if we take a look at the quark content of a proton, to make up a proton, we need 3 quarks, since the proton is a baryon. And those 3 quarks are going to be the up and the down. And in fact, we're going to need 2 ups and 1 down. And just to kind of summarize this real quick, if we look at the charge, if we're going to make a proton, we know the charge on a proton is +1, and the charge of an up quark is 2/3, and the charge on a down quark is -1/3. So if we add those together, 2/3 plus 2/3 minus 1/3, we get 3/3, which is equal to a +1 charge. And which, if you think about that in relation to the neutron, the quark content of the neutron, and think about what those charges would have to add up to. For a neutron, we have up, down, down. So in that case, we have a 2/3 minus 1/3 minus 1/3, which gives us a total charge of 0, and that is the charge on a neutron. So 3 different quarks are going to make up our baryons. Now, when quarks combine to form baryons, as I said, their charges are going to add up algebraically to a whole number, either 0e plus 1e or minus 1e. And that's going to be the same when they're also combined to form mesons. Charges are going to have to add up to a whole number, either 0e plus 1e or minus 1 elementary charges. And each of these types of particles, and there's a table here kind of outlining these, and these are different ones that are being discovered using experiments with the particle accelerator. And I'm sure next time we see Dr. Williams, he would love to expand on his knowledge and experience with all of these. If you guys have any questions, make sure you write them down and come get some answers to your questions. Hope you all have a wonderful day.